last time we started with autoencoders, and we started actually talking about PCA, right? And about the PCA, when we started, we talked about the fact that if we have a high-dimensional data, we can essentially represent it in a lower dimension, which we call it usually latent space, latent dimension. And we take that high-dimensional data, and then we use the properties inside the data to represent it with a fewer entries. And this is going to help us because then we can just reconstruct that high-dimensional data from a few components, the latent variable, latent representation, which is a more compressed version, right? So you can think of it as a compression idea. And we talked about PCA. So PCA was doing the compression, but it had one particular property, and that was that it was linear, right? So meaning that you could capture this dimensionality reduction in the data if that reduction is somehow formed in a linear form. Like the example we had last time, all the data is on one line, even though it's two-dimensional, right? Then you can do this with PCA. But what about this kind of data? Say you have a data set where your samples are all looking like this. So the first entry is sine of theta, the second entry is cosine of theta. Then what do you think about this one? Can I compress it into one variable? Can I just use one variable to represent this data point? No, I mean, looking at this one, you don't need to just do it mathematically complex. Just think what you can do instead of this one. Can you represent this guy with one number, the whole vector with one number? If I know theta, can I write down this vector? Yes, right? So theta is enough for me to represent this vector, right? Correct? So theta is a lower dimensional representation of this vector x, correct? So if I know theta, then I'm going to make a vector whose first entry is sine of that theta, the second entry is cosine of that theta, right? So the point here is that I can represent this particular sample or this kind of data with one single variable or latent variable. But if I use PCA, I'm going to fail. Why? Why does PCA fail? Yep.
Because the points are in different places and you can't just find a clean plane, I guess?
Clean line, right, in two-dimensional, hyperplane in general, right, exactly. So because the relations between these, or the representation of that latent variable, that is smaller variable, is not linear, right? So the variables are lying on that circle, right, the blue circle. Because every single first entry plus second entry squared is going to be 1 always, right? So this x is a point on this circle, but PCA can only find a line, right? So it's going to find the line which is covering most samples, right? And then if you do that, whatever you put your line, it's going to always collect just 2 points, right? It cannot collect more than 2 points, meaning that PCA is going to fail doing the low dimensional representation here, right? So but if I could essentially represent it with a nonlinear, if instead of PCA I was able to do the compression and decompression by a nonlinear process, then I might be capable of representing that low dimensional representation, the latent representation. How can I do this? Let's just think of this architecture. So look at x1. x1 is my first variable inside x. So I told you x is sine of theta, and here is cosine of theta. Okay? Now, what I am doing, x1 is essentially sine. So this guy is x1. This is x1. The cosine is x2. So what I am doing, I am taking x1, I am multiplying with 1, and then add it up with x2 with 0, right? So after doing this, essentially I just have at the input before activation here in this neuron, x1, right? And x1 is sine of theta, right? Correct? Everybody's following? Yeah? Sorry? I just wanted to do that, just to show that I'm capable of doing it with a nonlinear architecture. So it's my suggestion. Why should it be 1? Yeah, but then you're going to have sine plus cosine. I don't want that. Yeah? I just want sine, right? So I'm going to just multiply it with 1, multiply this guy with 0. Now at the input before doing activation. So think of this guy. This is a neuron, right? And then what you get as the input before doing activation is the weights multiplied with the input added up, right? Which is going to be sine of theta, right? Now I am going to activate it with the inverse of the sine function. So this arc sine is going to just give you the argument, meaning that arc sine of theta is theta, right? So what do I have here at the output? That is theta, right? Now if I want to get this theta and I want to decompress, get back to my own signal, to my own vector x, what should I do? I'm going to get this x, and then I give it to 2 neurons. Both of them are having weight 1, right? Theta multiplied by 1 going to be theta here. When I compute the sine, this is sine of theta. This is exactly x1, right? Theta multiplied by 1 here going to be theta. Cosine of theta is x2, right? So now I am able to get my signal x1, x2, compress it into theta, and then from theta I can get back to my x1, x2, right? So what is different here as compared to PCA? Nonlinearity, exactly. So the neurons that I have here in the PCA, they were linear, right? So I was not doing any activation here, here, and here. Now I am doing activation. So you see, simply just adding activation, nonlinearity to the neurons, you can do more, right? You can do much better as compared to the case of simple linear PCA, right? Everybody's clear? And of course, again, like PCA, you can think of the case where you don't have your data perfectly on the line, on the circle. It could be randomly a round circle. But again, if you use this architecture, you're going to get roughly a good estimate of the points, right? So it's going to do the dimensionality reduction for you with a nonlinear transform, which is more powerful as compared to the linear transform, right? Now, this architecture, if you look at this one, do you remember of something before we had? I am getting data, x goes in, then I am encoding it, I get some bottleneck, and out of that bottleneck I am decoding it, right? Did we have such an architecture before? Yeah, the sec-to-sec model, right? Encoding, getting the bottleneck, decoding, right? So you are again doing this here in the autoencoder. So in this nonlinear PCA, you essentially start from your data, do some encoding. That encoding is going to compress your data in a very tiny space, right? So your image is a huge, say, ImageNet image with 150K different pixels, right? Then you compress it into only 100 pixels. And then when you want to reconstruct that image, you again decode it, right, with another neural network. And that neural network is going to give you back your high-dimensional image, right? So this is essentially what we did before, and we can do it for this task as well, because this is the same thing. We want to encode the data that we have into a very tiny space, and then from that tiny space, we want to be able to get back to our data space, right? Now, as I said, if your data is not perfectly on the circle, you still can do the same thing. So you can potentially train such an architecture. So this architecture has some nonlinear activations here, some general weights. You can try to find those weights perfectly or optimally, such that the error between what you have, x1, x2, and what you recover as the estimate of x1 and x2 is minimized, right? This is again a kind of simple neural network, and you can simply train it by defining properly your loss. And this is what we are going to do today for the rest of this first part, okay? So Of course, if my data is of this form, when I just train, I'm going to end up with one circle, right? So this theta is essentially representing this circle because, well, I cannot do more than that circle with one dimension, right? But that circle is going to be a kind of very good estimate of your, a low dimensional estimate of your data, right? So you are getting a bit of error here, but that's okay. I mean, you're as a reward, you are getting lower dimension, right? You're reducing the dimensionality. So in general, you can always think of this PCA problem in general in a nonlinear form. So instead of having those linear transforms, W1, W2, and W1 hat, W2 hat only, you can add some activation. Or you can even replace those encoding and decoding architectures with two arbitrary neural network that is feeding your problem, right? So you know what is the input dimension, then you know what is your target latent representation dimension. So you can make one neural network which takes that input, brings it to the dimension that you want, and then from that dimension, you want to get back to your input dimension, image dimension, you just put another neural network, which is your decoder. And this is the general architecture which we call it encoding, auto-encoding. It means that it's somehow encoding the data itself and decoding it back, right? So it's not encoding data to transform it from one shape to another. It's just transforming data to itself, but in the middle, in the bottleneck, it's capable of doing a latent representation, a representation which is potentially very low dimensional. Everybody's clear? Questions on that? No question? Yeah.
So I guess I was wondering, what would we be, like in the example we just had 1 and 0, you just have to learn and...
In general, you have to learn it, of course, yes.
Oh.
Yeah, that was just a dummy example, right? Okay. But in general, you can have a neural network here. For example, here is a CNN, right? So you have input image, which could be very high dimensional, and then you can bring it down to very tiny dimension, maybe 100, maybe 10 even, 10 latent vectors, a vector of size 10. This is your latent representation. So you have one CNN here, and you have another CNN here, which takes that 10-dimensional vector and brings it back to your image dimension, right? And now you want to train it, you need to define the proper loss, which we are going to do, and then you can just do back propagation to train. No? Clear?
I mean, I guess I'm still sort of struggling to see, like, I guess I sort of got the circle, but comparing it to the, like, the circle seems way more, I mean, the image seems way more...
More intuitive, of course, than this one. But let's just try a couple of things. Maybe it gets more clear for you. But the point is that, I mean, I'm going to explain you through the lecture today. So no worries. Yeah? Okay.
I'm still quite curious about how to interpret the original X and its outcome from the X hat. Like
this one and this one?
Yes.
This one is estimate of this one. So ideally, this one is exactly x1. But like in this example, it's not going to be exactly x1. It's roughly x1. And then you try to make that error as small as possible. Because this is like 1 pixel of your image, and you want it to be exactly the same when you decompress, right? Okay. Yeah, it's the same thing. Yeah. Questions? No question? Yeah.
Quick one. So, how can we know how far we can compress by dimension fully?
Yeah, this is I mean, in general, it's a hyperparameter. You need to play with it. But, I mean, for most data that we have, you can do it as small as you want, pretty much. But you are losing a bit of quality. I'm going to give you an example. For MNIST, for example, if the input is MNIST image, you want to recover it, you can even do it with dimension 2. So this is what Bruce did yesterday, right? Sorry, Tuesday. So yeah, you can do it as small as 2 even. But of course, I mean, the quality is going to drop gradually, right? The lower the dimension gets, the worse the quality would be. But you still recapture the same property of the image, right? And this is because every data that we have in the nature is somehow in some domain, this is low dimensional. This is what we know, right? So we know like a data, an image has a finite amount of information. And since we can represent that finite amount of information with tiny random variables, this means that that tiny random variable is somehow capable of encoding this whole image into it. But how we can do it, we didn't know up to the point. I mean, we did know for a few specific data structures, like in image processing, video processing. But this autoencoding was a kind of breakthrough because we didn't really need to know analytic form of that transform. We can just learn it. And this is doing the job. No worries. Questions? OK, great. So now the whole task of one autoencoder is that you have encoding and you have decoding. And the whole task is to get your input image. You convert it into a latent representation. That latent representation is always, in terms of compression, it's always much smaller than your data dimension. And then from that one, this latent representation is somehow capturing the principal features of your data, which are sufficient enough for you to just decode this data back. So to just get from that principal features back to your data. So this is what we call it autoencoding. Latent representation is somehow borrowed from the terminology we used it in PCA, but is a kind of very, common terminology when it comes to generative models, because like GANs and also diffusion models, all of them always work with latent space. And latent representation simply means that you have a data which is a very visual for you, for example, an image that you can simply see it, but there exists one imaginary space where this data can be represented with a few numbers, right? And that space, we usually call it latent space, right? And that captures all the information, but that space is not visual for you. That is good for computation, but that is not good for our visualization, right? So this is the idea of latent representation, and any autoencoder is always containing one encoding and one decoding, exactly for the same purpose that I told you. So this kind of architecture that we have here is what we call it vanilla autoencoder, and its main purpose is to just compress the data. But you might ask me, is compression so important that the architecture somehow got a name? Well, there are two answers to this. The first answer is somehow naive answer, and at the same time, either very naive or very deep answer, and that is yes. Because like people like Hopfield, if you know him, the one who has Hopfield model, one of the key figures in linguistic and artificial intelligence, he believes that when a model can do the compression, it can learn. Like the whole intelligence is summarized in compression, for example. But this is not the only, if we want to be a bit more practical, the actual answer is then actually using autoencoders, we can essentially do more than compression. Pretty much we can somehow play with the data as we wish, and at the very end we get an idea how we can even generate new samples using this compression idea of autoencoders. Okay? So now let's just get into a general approach for autoencoders. So in general, if you have an autoencoder, this means that you want to get a kind of representation of your data. And how you do it, you always design one encoder, one decoder. The encoder should be of the dimension. The input should be of the dimension of your data. The output should be of the dimension of your target latent space, right? And again, the decoder should be the latent dimension to the data dimension, right? So this is going to always be the case. The only key factor in designing an autoencoder is that how exactly you define the loss when you want to do the training. Because what you know is that you're going to give one input to it, and the input is what you choose, right? You're going to get one output to it, again, is what you choose, and they are usually your own data, right? Your image goes in, your image goes out, right? But when you want to start doing the training and finding out what are the parameters of the encoder and decoder, you need to have a loss function, and this loss function should somehow capture the whole loss you have end-to-end in this system. So this is the key point in autoencoders, and what we usually do, we're going to look at the target application that we have, and we see what are the conditions or constraints we want to satisfy. For example, in the vanilla one, which we had here, what was the constraint that we are looking for? What do we want to do with this architecture? If I give one image X to my encoder, what do I want? Output exactly X, right? So but the neural network, the decoder, is not going to give me X. It's going to give me something else, right? Call it X hat. What do you want to do then? Exactly. So you're going to define the loss to be the difference between those two, right? So this is the way you do it in the vanilla one. So you always want to have a reference, because we don't have a reference for latent representation. You don't know what is the perfect latent representation of this image. So we're going to make the decoded version, the output, and that is the reference for us, right? So we're going to look at that output, and we try to compare it to our data, and we try to minimize it. This is indirectly also controlling the latent space, right? So the latent representation is going to be trained in a way that is capable of reproducing the image itself, right? So this is the key idea, and how we should choose the exact reference. So in the example we had, it was because we wanted to do compression, so we want to be able to reconstruct our image. Then the reference is going to be our true data, and we compare it against the output of the decoder, but it depends on the target application, and we are going to do a couple of them today, okay? The first one we already have done is compression. I only want to break it down for you. So compression idea is that I want to get one autoencoder, and I am going to find the latent representation. What do I want from that latent representation? To compress my data, right? So I want to do compression with this architecture. This is my target application, right? And now, since I know what is my target application, I am able to define the loss in this architecture, right? So what does it mean? It means that I'm going to get my data X. I pass it through one encoder. I'm going to get the latent representation, right? So, for example, in the example you had on Tuesday in the tutorial, this guy was Amni's image, so it was 28 by 28 image, right? Gray image. It goes in, and then the latent representation was a vector of size 2. So you can put one simple MLP, this is what Bruce did for you, but you can put a CNN as well. You can put anything here as the architecture. This is going to get your data and represent it with by a two-dimensional vector, right? And then once you pass your data here, you're going to get your latent. From latent, you're going to get your recovery X hat. And what you want your recovery X hat to be as close as possible to X. So now, what you're going to do, so we wish to have X hat and X exactly the same, so we're going to define the loss to be proportional to the difference between these two, right? So it could be any loss function which is proportional to the difference between X and X hat. The simplest one, the difference of the norm of the difference between these two tensors, right? You can do it. So you just subtract pixel by pixel, sum them up, the square root, to power 2, and then sum it up, and then you try to minimize that guy, right? And this is going to make X hat as close as possible to your reference data X, right? So this is the idea. Now here, in this particular architecture that I explained, do I need any specific behavior on the latent space? Do I care like whether my latent space has negative values or positive values? Do I care about that? No, I don't care about it. The only thing that I care is that the dimension is fixed as I have fixed it, right? So I don't care what are the values inside the latent representation, and because of that, I really don't need to enforce latent representation, this Z, to show a specific behavior. I can forget about it. My loss is going to be only dependent on this difference, right? And this is going to indirectly enforce my Z to be in the specific dimension and be able to represent my data, right? That's it. I'm not doing anything on this one. Now, if you want to do training, that is now quite easy for you, right? So what you're going to do, you're going to start by passing x through this architecture. So x goes, you find z, z goes, you find x hat, forward pass is over, all the variables are known, then you start to do backpropagation, right? So we are going to just do forward pass till we get to the output of the decoder, and then when we want to do backpropagation, we start from here, right? We do know the loss. Loss is the difference between x hat and x, so we can compute it. This is a function of x hat. We can compute the gradient of loss with respect to x hat, right? And once we do it, we just start going backward through the decoder, right? So it's a CNN, a typical CNN that you had before. You can simply do the backpropagation by doing convolutions and linear transforms and reverse activations, right? So once you have done this, you're going to end up with the latent space. So at that point, you are going to have the gradient with respect to the latent space. This is the output gradient that you have in your encoder, right? So you keep on going backward on the encoder till you get to the very input of the encoder. At that point, you're going to have all the gradients in these two encoder and decoder architectures, right? And now that you do it, then you just update all the weights using gradient descent, and you keep on doing it, right? So everybody's clear. We are doing the training end-to-end, right? Exactly like seg-to-seg models, you're not going to train your encoder or decoder separately, right? Because it doesn't make sense. You want them together, yeah? So they should be somehow the twins. One of them is learning, at the same time, one of them is learning how to encode, and the other one is learning how to decode. They cannot do it separately, of course, right? Everybody's clear, right? Great. So one example, this is the one I guess Bruce solved for you yesterday. I keep saying yesterday, sorry, Tuesday. So Bruce did it on Tuesday, and the thing that he was doing was he was taking one MNIST image, and this z was simply two-dimensional representation, right? So a vector of size 2, z1, z2, right? And the good thing about it is that now you can even visualize it, right? So you can plot it in a two-dimensional space, right? So this is one of the key usages of autoencoders when you want to represent your data in a very tiny space. And you might say, why should I do that? I'm going to explain it shortly today. Okay? Now, the idea is that you start with, okay, you can put any MLP here. So this is going to get this 28 by 28 dimensional input. And then you're going to convert it in 2 dimensions. It could be as small, as shallow as one hidden layer, or it could be very deep. It doesn't really matter. When you get here, again, you put one other MLP, and this is going to take this 2-dimensional space into the high-dimensional 28 by 28 space. And then what you want that the very output is exactly the same MNIST image as the one you have given to this architecture, right? And this is not hard for you to just do the training here then. You just compute the loss, the difference between the two images, the one recovered by the decoder and the true image you have inside your data set, and then you try to minimize it, right? That's it. Everybody's clear? So in Python, you're going to be few lines of code, right? Define your encoder, define your decoder, pass forward over your encoder, get your latent, pass that over your decoder, get your decoded one, compute the loss to be the difference of two, the MSE, and then just do backward, right? Go backward till the input, right? And then give it to the optimizer. It's going to do the optimization for you, right? Few lines of code, and you can do it. It's easy. Just look at the tutorial, last tutorial. Okay? Now, that's going to be this. So this is the extra illustration. For example, you can have, this is my suggestion because the example I sold, the images you see here are all generated by this example. So we have 4 hidden layers for the encoder and decoder. And, well, you can just do it. So I don't need to repeat everything. For loss, you can basically use as simple as this one, right? So you get your decoded version, and then you compare it. You just subtract it from your original one. This is your loss, right? And then you try to minimize it. That's it. Yeah? And you're going to see that this 8 is going to look like this one, meaning that 8 is going to be represented almost perfectly, right? The data is not huge. It's just 784 dimensional, but you are getting from that close to 800 dimensions to 2, right? The compression factor here is 1 by 400, right? So you are just compressing by a factor 400 here. That's huge. And you might think it was pretty much impossible because we didn't know that this data is that sparse, right? Well, those who work in image processing, they have the feeling because the data is basically just a white background and a kind of curvature of black, right? And that's going to have a huge sparsity. But the question is that where I can find that, hugely sparse representation. We didn't know that, but this one is going to do it for us very, very efficiently without any need to find out what are those representations. Everybody's clear? So, any question on that? So everybody got the idea how we can compress with autoencoders, right? Yeah.
Sorry, in the previous slides, it says that no batch normalization is needed and also.
Yeah. This is in this example. I mean, you can do it. It can help more. But even for this particular example, even if you don't do any of that, just the most basic MLP, you implement with that one, it's going to do the job. Yeah, but if the problem, of course, is more advanced, you need all of those things. Right? No worries. So, questions? Okay, so that's going to be it. So it's another example. So this 7 has gone into this guy. Then I did the compression in 2 dimensions, and then I just recovered this guy. You see that this one is a bit more blurry version of this one. Yeah, this is because I'm using only 2 dimensions, right? My latent representation is 2-dimensional. But if you, instead of 2 dimensions, you use 10 dimensions, then pretty much you cannot say the difference with only 10 dimensions. That is still a factor of 40 compression, right? As compared to your input. Okay, so that's it about the compression. One thing that you should keep in mind when you are doing compression, autoencoder only makes sense when your latent representation is smaller and in practice much smaller than your input dimension, right? If that is the same dimension or more, then it's useless, right? Because what you are doing essentially, you are trying to encode your input, right? And then after encoding, you want to decode the latent, and then you want to end up with the same thing, meaning that this encoding and decoding all together, you want it to be a kind of identity transform, right? So it's like you get your image and pass it to the other side. You want this to happen after encoding and decoding. And if your latent space is as large as your data or even larger, this is not a hard thing to do, right? So the encoding, you can do the encoding by setting z. Say z is exactly the same dimension as x. Then z, I can set it exactly x, and I set x at exactly z, right? So x itself goes to z. Z itself goes to x hat. X has gone to x hat, right? If z is as large as x, then I can do it, right? And I don't need any neural network. So you are not going to train a big neural network with the latent space being larger than the input. Everybody's going to laugh at you, right? Because you could do it without any computation, right? You could get your image and pass it the other side. So it only makes sense when the latent space is very small, right? That is where you are doing some sort of magic, right? But if you're not doing that, then there is no magic here, and you're just wasting computation. You should feel guilty about all of those power you spend on that computation, right? All of this carbon dioxide being emitted for that purpose, right? So you don't do it, right? Great. So that about this. So this was the first application, the compression. But what is the second application? The second application is to just give a sparse representation of your data. And what do I mean by sparse representation? So, where's the chart? Okay, what is the sparsity of this vector? What is the sparsity of this vector? What is the dimension? 1, 2, 3, 4, 5, 6, right? How many of them are non-zero? 4. This is 4 sparse. This guy is 3 sparse. This guy is 2 sparse. This guy is 1 sparse. The sparser your signal or your vector or your data is, the more 0 it has, right? This is what we call sparsity. You sparsely see something non-zero, right? Now, why sparsity is important? Anyone has a clue? Yeah.
I guess because if many things are 0, so much of the dimensions are not changing anything.
Yes, exactly. And then when something can be represented with a sparse representation, this means that it can be very well compressed. This is the first idea. So as I told you, compression is pretty much everything. But not only that, the other key idea is that when something can be represented with a sparse representation, then this means that you essentially have a few components, few, say, entities that can regenerate that data, right? For example, if you have a sinusoid in time domain, a signal, which is a periodic signal, sinusoidal signal, right, in the time domain. If someone naive, someone without any mathematical background, look at this signal, this is a quite rich signal over time, right? Because it's changing all over the time, all of those values going up and down, right? But all of you know that if you do know what is the frequency of that signal, you essentially don't need anything else, right? Correct? So if I know that if my signal is of the form of cosine of omega 0 times t, if this is my time domain signal, I only need to know omega 0, right? Once I know it, I can regenerate it. I don't need to save all the time domain samples, right? Even though this guy in time domain looks like this, and one might tell you at least within the one period you should sample a lot of samples to be able to recover it. But I would say no, I don't need that. I just need this guy, right? So essentially the whole signal in time domain can be represented with one guy alone, right? Now, anyone knows about Fourier transform? Do you know how you can compute the Fourier transform of a sinusoid? How does it look like? If you just get a Fourier transform, if you don't know what is that, you can check it later. So if you compute the Fourier transform of this guy, which is a kind of like a kind of nonlinear function, say, okay, operating in this one, then this is going to have only one entry, and that is going to be at omega 0. Your signal in time domain is not as sparse, but in frequency domain is extremely sparse. Now, if you have two of them added together, like sine of omega 1t now again, this guy is going to be even more complicated than that one in the time domain. So it's going to look like something like this, right? Something like this, for example, right? So it's going to get more complicated. But again, you can only represent it with two entries, right? The frequency of every single harmonic that you have here. This is exactly what happens to your voice, right? Your voice, if you plot the time domain signal, it's going to be like crazy, right? But that has just a few components in frequency, right? So there is one tone in the one tone like ah, the other one oh, and all of the voices is a kind of combination of these tones. So if you know which tones are in the voice, then you just add those sinusoids together and you're going to generate that voice, right? So if you can represent some signal sparsely, this is very good because later on you can, first of all, you can compress it very perfectly. And secondly, you are more capable of regenerating that. And this is why we are interested in representing sparse things. So how you can think of it, for example, if I have one signal, one input, one data, which is 100 dimension, maybe I just want to represent this signal with another 100 dimensional vector, which is very sparse, like a few entries are there non-zero. Why it is important? Because those few entries are able to just regenerate my non-sparse input, right? Exactly like the time domain thing here, right? So if I just know that I need only two guys, okay? So in the frequency domain, again, I can think of a very high dimensional signal, right? High dimensional vector, But that vector has only two entries being non-zero, omega 0 and omega 1, right? And the rest of them are 0, right? That's great, because I can regenerate that signal now, right? So this is one thing. You can also add compression to that. That is also possible, right? For instance, I don't want to just represent my 100-dimensional data with 100-dimensional sparse latent. I want to represent it with 80-dimensional sparse latent, okay? And you can again do it here with the sparse autoencoders. Now, the question is how we can compute the loss here in this case. And there are two things that we should pay attention to. The first thing is exactly as before. So when we do autoencoding, we want the input and output to be the same, right? You just want to get a sparse representation of that, right? So you don't want to ruin your signal, your input itself, right? So the image should be the same as before. So I need to care about that thing as before, but also I now need to have my latent representation to be sparse, right? And if I do it with the vanilla autoencoder that we had before, there is no guarantee that that guy is sparse, right? That guy could be sparse, could be very dense, right? There's no reason for that. So how can we do it? We can use sparse autoencoders. So essentially, one sparse autoencoder is again one encoder, one decoder. You have your latent space. You specify the dimension of your latent space. In this case, your latent space could be as large as your input. It's even possible because maybe you are not looking for compression in terms of dimension. You just want to find the sparse representation, right? So it could be in this case. Now, X goes in, you get the latent. Latent goes in, you get the decoded version. Now, the question is, what do we want? First of all, we want our recovery to be exactly as the input, right? We want this to happen, so our loss should contain one term which is proportional to the difference between X set and X, right? So that should be there. What is the second thing I want to do? Sparsity. So I want to have my latent representation to be sparse, meaning that what should I have in my loss? And I don't want you to give me any specific function. Just intuitively tell me what kind of term I need to add to my loss. I need to have inside my loss. More zeros, exactly. So I need a term which is small when I have a lot of zeros, which is large when I don't have lots of zeros, right? Then when I minimize it, I am increasing the number of zeros as well, right? Correct? Exactly. So what I want to do, I want to have one term which is also proportional to the sparsity of my latent representation, right? So I want it to be very, very sparse. So it means that I want to have as least as possible non-zero entries. So if I can make something proportional to the sparsity, then I add it to my loss. This is going to do the job for me, right? And this is pretty much the regularization we did before, right? So now we are regularizing it with the number of non-zeros, right? To just make it as sparse as possible. So loss is proportional to these two, difference between X and X hat, and also is the sparsity of Z. How can I write it down? Well, the difference between X and an X is not a hard thing to do, right? X and minus X, that's it. What about the sparsity? Anyone has an idea? We talked about it once before, yeah?
Just count the number of zeros? I guess the number of things that are not zero?
Not zero. Yes, this is one idea, but this is not a good idea. Can you guess why?
Well, I guess it probably wouldn't be related to whatever, like it could just be some unrelated number and it would like overflow.
No, it is related because it is counting the number of non-zeros inside Z. So it's actually a very good function. The issue is that we cannot use it in practice. Do you have any idea why? Can you compute the gradient of that function?
Oh, yeah, you can.
You can't. Yeah, this is the issue. Yeah, if we could, then this would have been the optimal one. But any other idea, any function that we can compute the gradient, and is also somehow proportional to sparsity. Square is not very proportional to sparsity. Do you remember Lasso? Lasso regularization, right? We were regularizing our model with what? What was that function adding to the loss? Absolute value, or I mean general L1 norm, right? Exactly. So that is the idea. So you can put S here. This is the function which is proportional to sparsity. And it could be any function. Then you can add some regularizer here. This is a hyperparameter. This is your choice. You need to tune it by doing experiment and validation. How I can choose this S? Okay, this is the first suggestion your friends said. This is what we call it L0 norm. L0 norm, it means that you look at this guy and say how many non-zero entries are here. So what is the L0 norm of this vector? 1, exactly. What is the L0 norm of this? 2, exactly. So it doesn't matter what the number is. You just count the number of non-zeros, right? This is not really a norm mathematically, but we call it norm. Okay? So it's L0 norm, but the issue with this guy is that you cannot compute the derivative, right? It's like a step function. So it just jumps from one point to another. And it's not a good function in terms of gradients, so we cannot use it. The good one is the good convex approximation of it is L1, which is also used in Lasso. So if you put L1 norm of Z here as well, it's going to do the job for you, right? At the end of the day, you're going to end up with one latent representation, which is sparse. And how sparse that is? Well, you need to tune this lambda. Okay? You just make it as sparse as possible by tuning the lambda. And of course, this comes at a trade-off, right? The sparser you make it, the worse going to get your reconstruction, right? But yeah, this is, at the end, your choice, which point in this trade-off you want to stay, right? Okay, questions? Everybody's clear? No, it's absolute value. Absolute value is convex, right? Is pairwise linear, right? So it's convex. But it's not always differentiable, but you can define subgradient. So that's going to be no problem. Now, one other choice is this one. It looks a bit more complicated, but just to have it, just to have heard of it once at least. So the idea is that you compute a kind of empirical distribution on this Z. So you're going to count the number of non-zeros and you count the number of zeros. Then you think of this whole Z, which could be a tensor, for example, to be or the vector Z like this guy here. You're going to say, okay, here I have 2. 2 out of 6 is non-zero, right? And then I'm going to say this is the empirical distribution is Bernoulli 1/3, right? Because 1/3 is non-zero. So you think of that empirical distribution here. You also put one Bernoulli distribution here with factor rho, and rho is again the hyperparameter, and you compute the KL divergence. I mean, I'm not sure if you all know what is KL divergence, but it's pretty much something like the cross entropy that we had. So you get two distributions, and you compute the difference between them. And when you minimize it, you try to make this PZ exactly like this guy, meaning that you make your Z to be sparse like Bernoulli with chance of 1 being rho, right? So you obviously can say that if rho is very small, then you're going to get a sparser, right? That's it. Yep.
So what's the problem here that we do not also consider the L2 norm here?
L2 norm? Because L2 norm is not forcing 0. It's just forcing the values to be small. Right? So L0, I mean, here, L0 for this guy, right, is the same as L0 for this one. Right? Sorry, L2, right? Yeah. Or maybe different. Sorry, it shouldn't be. No. That's going to be 0.04. No, I was not. No, I'm doing a mistake. Yeah, but you get the idea, right? So yeah, you do the calculation. So you can change it, and then this is going to be the same thing, right? And because of that, this is not doing this. But I mean, it does some job for you, right? So it's going to make the values smaller. Then you can ignore some of them. But it's not going to give you zeros exactly. Okay? So the whole beauty of this lasso is that Tibshirani could prove that when you use this, you're going to get absolutely zeros there. So there are zeros. This is why we call it lasso, least shrinkage and selection operation, right? It selects, it puts some of them to be 0, right? This is the whole magic of losso. Any question? No question? Okay. Yeah. So if you want to train one sparse autoencoder, that is again quite easy for you. So you put X here, you're going to send it to the latent, and then from latent to the decoder. And now the first thing is that once you're here, you start to just do backpropagation, right? And when you want to compute the gradient at the very output, you only look at this loss function here. So your R hat, your sample loss, is the loss between X hat and X and something related to Z, right? So when you start to backpropagate, you're going to compute the gradient of this guy with respect to output X hat, right? And that other term is not showing up, right? It's not doing anything here, correct? When I compute the derivative of this loss with respect to X hat, the second term I treat it as a constant, right? Correct or not correct? Yeah? So that is not going to change your backpropagation on the decoder, right? So the backpropagation on the decoder is exactly as before until you get to the bottleneck, to the beginning of the decoder, right? And once you got to the beginning of the decoder, the next thing that you want to compute the gradient of your loss with respect to your latent, right? And then you would say, okay, I have one gradient coming from X hat up to this point, right? This is what you get with your normal backpropagation, right? Which I can simply, again, backpropagate it because I can compute the gradient of X hat with respect to Z, right? This is what you did inside your backpropagation. But there is also one other term here. And that other term is this sparsity term, right? Which is now depending on Z, so you need to compute the gradient of that one as well. So somehow like what you do in skip connection. When you do a skip connection, you move backward first, you don't see any difference. But the point where everything got branched out, you're going to have that extra gradient showing up. So this extra gradient is showing up when you're at the bottleneck. Again, you have the gradient here, and then you push everything backward, right? You go backward till the input. So the only change that is going to happen to the normal backpropagation is going to be this extra term here. I mean, I do know that you use PyTorch or TensorFlow and you just ask it to do it, so you don't really implement it, but it's always good to know what is going to happen, right? Because at the end of the day, these gradients are the guys who are, propagating information for you, right? Okay, so, and once you did that, then you just need to update for multiple rounds of gradient descent. That's it, right? Sorry. The architecture is going to get trained. Yeah? So this was the second application. The last application before we get into data generation is the idea of denoising. This is the most interesting application nowadays people think of, right? So many of you might have. I give you a gray image. I want you to just convert it into a color image, right? And we can do it nowadays with machine learning. It's a magical thing. No, it's not. It's just an autoencoder. You exactly do the same thing with that one, right? So denoising means that you have what you want to just refine a noisy data. And what you can do, well, if you have, intuitively, or if you want to think in terms of information, you want to say, okay, as long as the data has enough information, which is contained in the color version of it or non-noisy version of it. Now, if I can get from this noisy version to the right latent representation, then the decoder is going to take me back to the good image, right? The only test we need to do is this one. And again, we don't want to really find the explicit expression for these encoding and decoding. We just learn them, right? We train them. We put some architectures there, and we just do the training till we get it. This is exactly the same idea. So applications, for example, you want to remove background noise in one image. You want to just increase resolution, like a tiny image. You want to improve it, like high resolution image. This is things that nowadays are very easy to do with all of these neural networks. And you can color gray images, like I give you gray image of some scene, and then you just change it to color. Of course, it's not going to be exactly the color image, but it's still having a meaningful colored version of that image, right? And lots of other things you can do with that. And of course, you cannot still do it with vanilla autoencoder, because in vanilla autoencoder we just give the image itself and try to decode that image. But you can guess how I can do it with autoencoder. What should I change in my architecture now? So if I have a bunch of images and I want to train one autoencoder which is able to denoise images, what should I do? I have the image. Can I make a noisy version of it? Yeah, I add a noise, right? I put in input. I try to make my autoencoder to give the image itself, right? Once I train it on enough number of data, now if I get a new noisy image and give to this architecture, it's going to give me the original image, right? Everybody's clear? So how can I do it? This is the kind of autoencoder that we call it denoising, and you simply do it like that. So I have this cat image. This is a fine image, high resolution image. I'm going to make a low resolution, blurred version, noisy version, whatever I want, right? And I put it at the input, okay? I pass it through the encoder. I get the latent. Latent goes to the decoder. And then when I am at the decoder, at the output, what should I do? I compare that output to what? Not the noisy version, the original version, right? The fine image that I had. Now, if you want to formulate it properly, right, so this input could be anyone. So this is what I call it the degraded version of my image. So it could be noisy, blurry, gray version. Like if you want to color images, you get your color image, and then you just take the gray version of it, right? And then you put the gray version as the input. It goes through encoder, decoder, and once at the decoder you see some output, you compare that output not to the gray version, but to the original RGB image, right? And then you're gradually going to train this autoencoder to get one gray image and returns you the RGB version of it, right? It's not the perfect RGB, of course, because you're losing a bit of information, but at least it can give you some meaningful RGB image, right? So the colors are not nonsense, right? Maybe they are not the exact color, right? It's hard to guess from a gray image what is the color of my shirt, right? But it's easy to understand, like if you put it here blue, then, I mean, how the shadow gonna go on my other part of the shirt, right? So that architecture can do it for you, right? And then it chooses, for example, blue to just color it blue, right? And you don't care. I mean, blue, gray, whatever, right? So same thing here. So you just make a noisy version. You put it at the encoder, and then you basically try to decode it. And when you want to compute the loss, you're going to compute the loss between the original sample that you had, the color version, the high resolution version, whatever that was, and the output that you get out of your decoder. And yeah, that is going to do the job for you. So if you want to formulate it in terms of mathematical objects, say I have x. X is my sample inside my data set. So it's, for example, the tensor of the true RGB image, right? And then what I'm going to do, I'm going to make one noisy version of it called x tilde, right? X tilde is going to go inside my encoder. I'm going to get the latent representation. From latent representation, I'm going to do the decoding. I'm going to get x hat. And now if I want to compare x hat, I should compare x hat to the original one. Which one is here? X itself, not x tilde, x, right? This is the only difference to the basic version. So I need x hat to be x. Of course, I started from x tilde, the noisy version, but I want to just make it to be x. So basically what I need to do, I need to just define the loss to be proportional to the difference of these two. If I want to add a sparsity, I can add a sparsity by just adding that extra term. If I don't need a sparsity, I just ignore it, right? So at the end of the day, my loss function is going to look like this one, which is pretty much like the general form, right? So if you put lambda to be 0, you don't want a sparsity, you don't care about a sparsity, you only want to have your recovery to be exactly like your true sample that you had, right?
Does your original data come from the pure X, like the good image of the cat, and then you modify it to be the blurry cat?
Yes, yes, exactly. When you are doing the training, right? So you get lots of images, and you make it, I don't know, noisy, blurry, whatever. You make that, and then you start to give that noisy version to your encoder, and you try to make the output the exact sample that you have, right? If you do it on lots of samples, then at the end, if you now get one noisy image and you give it to your architecture, it's going to give you the counterpart which is not noisy, right? To anything, yes, because essentially whatever we are doing here is unsupervised, right? We don't have supervision. We're just building out some labels by ourselves, right? So we say like, I mean, you want to find the latent, right? And latent has no label, right? There is no true label for this one. This is why you do the decoding, because you want to get some guy which you can compare it to a reference, and that reference is your sample inside the data set, right? This is what you would do always in unsupervised learning, right? But there is no basic thing, of course. This is a hard thing is then how you can evaluate or test your model, right? So there are ways to do it, but it's not as simple as the case with supervised sets. Questions? Yeah.
I'm not sure in this application whether compression is critical or not. Like,
yeah, I mean, this is a good question. I mean, I would say if you're just denoising, compression is still important, because if you don't, it's like overfitting. If you put your latent space to be large enough, then it's going to capture principal features of the noise as well, right? And it could be that it gets worse in generalization, right? So tuning the size of your latent is also crucial here. So with your data set that you have, you might get same quality of the output when you are doing the training on small and then a large latent, right? But it might be when you test it on a new data, then the smaller one is generalizing better, yeah? But at the same time, if you just make it super small, then again, you get into the trouble, right? So it's a kind of hyperparameter tuning issue. You need to come up with a solution. But usually, I mean, you don't play with that dimension. You just play with the sparsity. So that's going to be easier, because it's just one hyperparameter, lambda, you just tune it, right? That is easier. Yeah. Questions? No question? OK, great. So summary of different autoencoders that we had. Vanilla one is the one we use for compression. You just get to the latent, which is smaller dimension. This is going to help you to compress. You could have a sparse autoencoder, which is just simply doing sparse representation of your data. And you can have denoising autoencoder, which is capable of getting a noisy version of your data and recover your data itself, right? So these are the three main autoencoders people widely use in practice. But these autoencoders have ended up with the fourth application, which is data generation. And by the way, data generation was not initiated here, but when people started to work with this, this was one of the intuitive architecture which gave us the idea, OK, maybe we can generate data. And I'm going to talk about it after a few minutes of break, OK? So, shall we go on? Just, yeah, to finish this one. So, the last application of autoencoders that we can do is data generation. And it might sound a bit crazy, but given the knowledge you have up to this point, I can show you that it is not crazy. I mean, I'm not giving you all the idea about data generation, but I am showing you that it's not crazy to do that. So, how we can do data generation using autoencoders. So let me just give you one quick story. Let's consider that we have MNIST data set, okay? And from MNIST data set, I am using only two kinds of samples. The samples of handwritten 1 and the samples of handwritten 8. I'm using this specific example because you can try it at home with the same architecture boosted on the last tutorial, okay? So I have trained this autoencoder, which takes either handwritten 1 or handwritten 8, and it can perfectly recover it, okay? And my latent space is of dimension 2, okay? I have only 2 dimensions, Z1 and Z2. Now, can I show latent space in a 2-dimensional space? Of course, I can just write down one Z1 here, right? And Z2 here. Z being Z1 and Z2, this is my latent representation. Okay? So this is the latent representation. Every single image that I have inside this data set, any of those 1 or 8, if I pass them through this encoder, I'm going to end up with a Z1, Z2, right? And then from that Z1, Z2, I'm going to reconstruct that image, right? Now, I can show those latent representations of the data I have in this space, right? In this dimension, 2-dimensional space. So what I can do, for example, like I send 1/8, right? 1/8 through the encoder, and when I do the encoding, then at the bottleneck at this latent representation, I'm going to get one vector of dimension 2, right? Maybe the values, I don't know, they are like Z1 is 4, Z2 is 5, right, for example. So it's going to be the point 4 and 5, right? And then I'm going to find that point, and I'm going to put a dot here, okay? Now, I send my next 8, I get another point here, next 8, another point here, and so on, right? So I start to see these points when I send 8. I also send my 1s, so handwritten 1s, and then I just draw wherever I see my latent representation. For example, I assume that I get like the first one when it goes to the latent space, it's going to give me this number, and so on, right? Okay, I'm going to see these points, and I'm going to see those points when I send 1 or 8. So this is what you see inside this, this diagram here. So I assume when I'm sending handwritten 1s, I'm going to get these points. So these are the points, the latent representation of different handwritten 1s. And this is the, or these points are the latent representation of different 8s. Okay? Everybody's clear, right, about this diagram? Because that is important. Okay, now, I got this guy, and then people, when they did this experiment, they started to see that, okay, the points which are showing latent representation of handwritten 1, they are somehow concentrated in one region. And for handwritten 8, they are somehow concentrated in another region, right? So is it a kind of property always happening? Like if I get any 8, I'm going to end up a point in this side of the latent space. And if I just do transmit 1s, I'm going to get a point around 0. Is it always the case? So this was a kind of interesting question they started to ask. And of course, there are always two kinds of people. There are some kind of practical engineers who, when they see this, they're going to practice and try to implement something. There are some other people like us, like people at the university, who are trying hard to just formulate things without touching the implementation, right? So first, those people, like us at the university, they started to recall this idea of having data space, right? So what is data space? So if you remember in chapter 3 when we talked about data space and data distribution, they say, okay, we started to assume that any handwritten 8 that we have, it has a kind of distribution, right? In that very large dimensional space. Meaning that when an image is handwritten 8, the probability of that happening is not 0. When the image is not a handwritten 8, then the probability is going to be 0, right? And this is in that large dimensional space, that 784 dimensional space, right? The point is that if I can sample all of those handwritten 8s, and again, remember, we don't have access to that, right? This is somewhere out of this universe. We never have access to all handwritten 8, right? But I assume that that was possible, right? If we can do this, then maybe when we send every single of them through the encoder and we find out the corresponding latent representation, they are going to show us one nice compact region. Huh? Maybe this is going to happen, right? They started to call it, okay, I don't have it, they started to call it the latent space of that data distribution. Like when I say latent space of handwritten 8, and I say that is here, this means that I assume in my mind that I have access to a data set which contains every possible 28 by 28 handwritten 8, and then I send all of them through this perfectly trained encoder, and I end up with the points within that region. Okay? And this is somehow compactly covered. It means that there is no spot left here, right? So I assume that. This is a very strong assumption, but you know, when you see such a behavior, you might say, okay, maybe this is the case really, right? Like any handwritten 8, when I do that, do the encoding, compression, you're going to end up that point, right? A point in that circle. Now, they started to do more practice, more examples, and they started to see, okay, maybe sometimes you see a kind of compact region, like all 1s are in this compact region. Here I have more samples, and here I have more 8s, so you see it like they are somehow concentrated in 2 different regions. And they say, okay, this is a good idea. Actually, latent space, it might be very compact. Yeah? Meaning that, again, if I just get all of those handwritten 8s, which I do not have access to, it doesn't mean that it's computationally hard. It's pretty much impossible, right, in practice. But if I could have access to them and I encode all of them, then I'm going to end within one circle here, right? Now, I don't have access to that, but let's say that I guess this is really the region. Can you tell me whether I can use this region to generate a new handwritten 8? Yeah, how can I do it? Just use decoder 1 at one point, which you did not see before, right? So I am guessing like that this region is the latent space of 8, right? But I have seen only these dots here, right? I haven't seen any point here, right? But now, if this is really the case, now I'm going to take this point, right, and give it to my decoder. This should give me one 8, right? And that 8 is actually one of those 8s which I did not have access. It was in the data distribution. I did not have access, but I didn't need it because I know the latent space, right? So I'm going to get this latent representation. This is easier, right, because it's 2 dimensions. It's not 784 dimension anymore. So it's easier to sample, right? I'm going to randomly sample one point from that region, pass it through decoder, I'm going to get 8, right? Great, I'm generating data. So they started to say that, so they said, okay, the good idea is that I get one new point from one region, which I guess is a latent space. Why I say I guess? Because I cannot really formulate or determine the latent space. If I want to determine latent space, I need to know exactly what the data distribution is. But the whole problem is that I don't know that, right? Correct? Distribution. So I'm guessing that that particular thing is the latent space, right? How I do it simply out of experiments, right? I do lots of experiments. I see everything is concentrated here. and then I just sample from that one, right? And they started to say, okay, I'm going to sample one point. I'm going to send that point through the decoder. And if I am lucky, that is going to be a latent representation of one of those handwritten 8s that I have not seen in my data set. And then the decoder version is going to be the exact handwritten 8, right? Now I am generating one handwritten 8 without seeing it before, right? So I am generating new data. It's a impressive task I'm doing, right? So so this is the idea of data generation. And why this is data generation? Because I'm just starting from a random seed. What is my random seed? The random point I take from this latent space, and then I give it to a decoder. Is generating data. So I am not deforming any previous data anymore. I'm not using any handwritten 8 anymore to generate this new one. I'm randomly choosing one point from latent space and generating that, right? So I'm just learning how to generate handwritten 8, which is a kind of, a great thing we could do. So people started to do this, and they did exactly what I told you on the board. So they started to just train this guy maybe only for 8 and 1. And so as I said, you can try it at home for this particular example with Bruce code, and this is going to work. Okay, not always, but most of the time you are going to get a kind of handwritten 8. And you're going to now take one sample point like this green point, which you have not seen before. So it's none of your previously seen latent representations. From that region, which you guess is the latent space of 8, and then you take it to be the latent representation of 1, 8, which you have not seen, and you do the decoding, and you're going to see some handwritten 8. And these images that you see are really generated. Like this is MNIST, and this guy is really the output of Bruce decoder. Okay? And you see this is 8. It's a bit different from a normal 8, but you can still read it 8, right? Correct? Okay. People started to try this. They get super impressed. They were like, okay, we are now generating, right? We are creators. We are not only just learning to mimic the behavior. So that was great, but the issue was that when they started to do this, even though the idea was very intuitive, this was very impressive, and this was working, when you train that model, then you start to generate, right? And once upon not that much of trials, you're going to get something nonsense. And it's not because your model is not trained perfectly. Your model is trained perfectly because whatever 8 you give to it, it compresses it perfectly. But the issue is that you're getting somehow invalid generation, right? When it comes to generation, the generation is invalid, but the compression is being done perfectly. Now, people started to think, what is the issue? Of course, again, there are two kinds of people. One kind, you are doing mistake. This is not going to work. You're stupid, right? This is one kind of people. They had been always there, like those who did not believe on backpropagation, who did not believe on, possibility of learning and memorizing, things like that. But there had been people who were more reasonable and tried to think out what is the issue. The conclusion was that the main reason is because of what we call the lack of knowledge about the latent space. You guess that your latent space is like this, but well, if you do a very exhaustive numerical experiment, you're going to see that your guess is very wrong. And the reason why you see this is because, if you remember in chapter 3, I tried to just count for you the number of images you can show in 28 by 28 space, right? Right? And that was gigantic, right? You can never ever think of that number, right? Now, how many samples you are going to do? 10,000? 1 million? 1 billion? 1 trillion? Okay, this is nothing as compared to the number of images you could have, right? So you are always, what we say theoretically, you're always walking in a low-dimensional manifold of your data space, right? So meaning that you can't just press your bottom a lot to generate samples, like you collect lots of handwritten 8s. But at the end of the day, when you compare the number of handwritten 8s that you have collected to the possible number, I mean, not exact number, but say a rough idea of the possible number of samples you could have, then this is one tiny drop as compared to an ocean, right? You cannot compare it. This is 10 to the power what? 10? That much samples you have collected? That guy is in order of 10 to the power 150, right? It's nothing. And it's like you just want to judge a Gaussian distribution based on one sample. You can never do that, right? So the issue is that we don't have enough knowledge of the latent space, and the whole thing that is happening is that when you just keep on doing more and more and more experiment, you see how naive was your initial guess. Because your initial guess is that this circle is your latent space. Then you're going to start to see that now with more samples it's going to look like this, right? And then at some point you're going to see that there is also one region like this here showing up. And then there is one region like this one showing up. So if you want to imagine what is happening, it's like you get a straw, you put it in the ocean, yeah? And you start to suck it in, right? And then you start, I mean, after 1 trillion years, you start to see one tiny island comes out, right? And then you conclude, okay, under this ocean, there is one single mountain, and the mountain is coming out, right? Okay, no worries. Just keep on sucking in for 1 other trillion years, and you're going to see other islands coming out, right? So this is exactly what's happening here. And this is the lack of knowledge you have. You cannot find out what is under the ocean by sucking that straw, right? This is the only thing that you are doing right now, sucking the straw. This is not a good idea. So the latent space turns out to be extremely asymmetric, and it could be hugely discontinuous, meaning that it might be that when you keep on practicing, you see like the latent space starts to deform into this one, right? And at some point, as I told you, there might be one red spot here starting to show up, right? So now the point here is that you have the feeling at this point that, okay, we got it. We got the idea that we can sample from this latent space and we can generate data. The only issue is that we cannot characterize the latent space, right? This is the issue. So yeah, maybe, for example, the sample that you are taking, and you are assuming, because you started to see a couple of samples around this circle, you started to assume that this circle is the latent space. But actually, this part of this circle is not the latent space, and you are just sampling from that one when you want to generate the data, then you are not getting one, right? So moral of the story, if you could have explicitly, or at least roughly, closely, approximately latent space of 1 or 8, you could generate all of them. There is no issue with your idea. The issue is that you cannot find out what is exactly that region, and our initial naive assumption that that region is very compact and well formed is not correct. It's not happening really. So that was the issue with the decoding and or generating the data. And then the question came up was that can we resolve this issue or not? So people come up with one idea which is quite impressive. It's one of the very nice ideas. I mean, when you get to the generative models, people really have done nice things. And generative models are one of the venues which I believe that it can somehow showcase the fact that knowing fundamentals is really important. Because every idea coming in this domain and is nowadays working comes from a theoretical background, right? So people started to think of variational inference quite some time before that, okay? And that idea of variational inference helped us to somehow resolve that issue. So what is the idea of variational autoencoder? The variational autoencoder actually uses variational inference, which is a kind of theoretical framework for estimation, that we somehow enforce this guy, this latent representation, latent space, to be compact within one region that we want. Okay? Now, what I'm going to do here, I'm going to just explain you how it works. Why exactly we should do it this way is a bigger question. I cannot say it here. Okay? But when we study like generative AI, and there we study variational inference, you're going to understand clearly why we are doing it here. But now I just try to explain it intuitively, because if you just want to implement variational autoencoder, you don't need all of those backgrounds, right? But this is the difference between an engineer and a practitioner, right? The practitioner only knows how to implement, engineer knows how to design it, right? If you want to be the engineer of generative models, you need to know that variational inference. So don't take me wrong, it doesn't mean that you don't need it. But if you just want to use it as a tool, you really don't need that one. So the idea here is that we want our latent representation to look like a Gaussian random variable. Meaning that I want that whenever I send A to the latent space, that representation in the latent space looks like I have a Gaussian machine, and then I just take one two-dimensional Gaussian variable out of it. Okay? I just want this to happen. Why do I want this? Because once I can make sure that my latent representation is Gaussian, then I can simply sample a Gaussian random variable, right? You can open your computer in Python, just write rand n, and then it's going to give you one Gaussian sample, right? So you can sample it easily with your computer. There is no problem with that. The only point is that I want to make sure that my encoder is taking me to a space where all the latent representation look like a Gaussian random variable, and then my decoder, starting from that Gaussian random variable, can reconstruct my data, right? So in particular, it means that I want my latent representation of, say, for example, all 8s to look like points here, right? All the points here, and this is the Gaussian distribution, right? So Z1 and Z2 are the two entries inside this Gaussian vector, and then I want it to be somehow most of the time at the circle of the bill, center of the bill, and then the probability of happening outside the bill, the main circle, is very low, right? I want this to happen. So how can I make it happening? Say I want to make this Gaussian variable here to be zero mean and unit variance, meaning that Z1 and Z2 look like two independent Gaussians, both of them centered at 0, and both of them have variance 1. Okay? If I want to do that, the idea is that, okay, when you are training, try to make your latent space look like that. And this is something that we do know how to do it in deep learning, right? So you just make you put your architecture a way that this happens, and then you keep training on samples till it gives you meaningful output. So how can we do it in this case? Well, say I have this 8, right? And this is the 1, which I want the latent representation to look like a Gaussian sample, right? So what do? I first gonna do encoding, right? I'm gonna give it to one encoder, the same encoder as we had before, but this encoder is not computing directly for me the latent representation. I am going to compute the mean value and a variance, right? And again, what is this mean and variance? There are two outputs, right? For example, in this case that I told you, we have two parameters, Z1 and Z2, right? How many means do I have? Two means, mean of Z1, mean of Z2, right? How many variances I have? Two variances. Variance of this guy, variance of this guy. So it's enough that my MLP gives me 4 outputs, right? And I take the first 2 as the mean and the second 2 as the variance. Okay? So I am not learning the latent representation itself. I am learning its mean and its variance. Everybody's clear? You got the idea? Okay, now, next what I'm going to do, I'm going to generate a vector z, which is random. I am not doing any, representation of or learning directly from those samples. This z guy is a normal, so I have one random generator on my Python, and then it's just generating me a Gaussian vector of size 2, right? That's it. But what do? I set the mean value and variance of this latent representation to be exactly the mean m that I computed and the variance v that I computed. So I am not directly computing the latent representation. I am sampling a Gaussian latent, but the mean and variance of that latent representation is the one which I computed with my encoder. Everybody's clear? You got the idea? So now I have one z, which is exactly the same z as before, right? Two-dimensional latent representation. I'm going to give it to my decoder. And then what I do, I try to make this decoder to exactly recover what I did, what I had at the encoding, right? I try to make it. But one thing, if I want to make the decoder, I mean, forget about this part in between, assume that this guy is directly connected to the other one as before. So if I want to make x hat exactly as x, what should be the loss? No, if I want x hat to be exactly like this one, how should I define the loss function? Difference between x hat and x, right? If I do that, I make sure that x hat looks like x, right? That's fine. But I wanted this latent representation, this guy, not only to be Gaussian, but also be Gaussian with mean 0 and variance 1. I told you that, right? How can I do that then? Following our discussion on sparse autoencoding. Add another term to the loss function, which is somehow enforcing your latent variable, your latent representation, to be 0 mean and unit variance, right? Exactly. So that's it. This is what we are going to do. So the way that we are going to define the loss, we are first going to say, OK, we want x hat to be exactly x. So we are going to have the loss between these two. And then we want this latent representation not simply being Gaussian, but we want it to be Gaussian with mean 0 and variance 1, right? Unit variance, 0 mean. Now, what I have here, this z, whatever that z is, this is Gaussian, right? Definitely, because I generated it Gaussian, right? I didn't generate or compute z directly from the output. I got the mean and variance, then sampled the Gaussian distribution, right? So this guy is definitely Gaussian. That is correct. But the issue here is that its mean is different. Its variance is potentially different, right? Now, I have one distribution. That guy is Gaussian with 1 mean and variance. I have another distribution that is Gaussian, 0 mean, unit variance. Two distributions I have. I want to make them exactly the same. How can I compute the difference between these two? Any suggestion? You didn't have it that much in the course. KL divergence, right? So you didn't have it that much in the course, but what is KL divergence? KL divergence is pretty much your cross entropy. Cross entropy is also capable of computing difference between two distributions, right? KL divergence is actually, you can show that KL divergence is cross entropy plus one entropy term. And KL divergence, again, takes two different distributions and compute the difference between them, meaning that when the distributions are exactly the same, then the KL divergence is going to be 0. When the distributions are very different, like you have a Laplace distribution and a Gaussian distribution, then the KL divergence is going to be high, right? The more different they get, the higher this difference is going to be. And KL comes from Kullback-Leibler. I mean, two mathematicians, right? But KL divergence is like my favorite thing in my whole life, okay? So if you don't know what is KL divergence, just Google it. It's like one of the most sophisticated things. Okay? You can show everything with KL divergence. Gibbs inequality, you can show it with that. Many of Shannon results, you can show it with that. I mean, that's crazy kind of metric people define. But what is KL divergence is simply the difference between this normal distribution and this normal distribution. And now, you might say, OK, if I compute KL divergence, how does it impact M and V? Essentially, when you compute the KL divergence between this guy and this guy, this is going to be at the end only a function of M and V. Okay? And then if you minimize this KL divergence, it means that you're going to push M and V to be exactly 0 mean unit variance. You might say, OK, why I don't just assume that M should be 0, V should be 1. You can do that, but KL is going to do it much more efficiently. Okay? So this is the only twist here for you, that why we use KL. Okay? But you just take it from my side, that you need to use KL. And again, in Python, you have KL divergence. You say that I have Gaussian with that mean and variance. I have Gaussian, 0 mean unit variance. And that guy can compute for you the KL divergence. That is a very well-established metric. Yes?
You separate the label kind of depends on the latent space is different, but if you force all of them to be the center circle, it's the same then.
It's the same thing as I told you, but KL is going to do it much better. Because the point is that those Z that I'm generating at the end of the day, they are samples. They are not the true distribution. I want them to be the samples of that distribution. So I don't want my architecture to wrongly interpret this distribution instead of Gaussian something else. When I put it KL, then I make sure that my architecture is really making my latent Gaussian.
So what's the output of your KL?
KL is a number.
But that number will represent the MMV.
It depends on MMV, and it's going to represent how much this normal MV is different from normal 0, 1.
So then you will have two different KL, so you can tell this is that label, the other one is that label, because their KL is different.
Sorry?
Because their KL is different, even though you push them to the center.
The KL is different. KL is different from 0, right? And when you try, this is in your loss, but when you keep minimizing it, then you're going to push KL divergence between these two to go to 0, right? Which means essentially your M and V are going to be 0 and 1, right? So they are going to be 0 and 1, but this is not the only thing happening. Those samples that are getting generated here by this random generator, they are going to look like 0 mean unit variance samples, normally.
Then how do you separate the label?
What do you mean by a label?
Because all your,
There's no label here.
I mean, different group. For example, this is 8, the other one could be.
Oh, right now I'm not talking about that. I'm just assuming I'm training one architecture to generate 8 for me.
Oh.
There is no one. Yeah, but that is something. I mean, you can condition it later on. Yeah, you can do it. This is a bit more advanced. I'm just talking about the basic idea, right? Now you want to just generate one machine, and that is just generating image of a cat. Yeah, that thing is a conditional generation. Yeah, it's going to be a bit more complicated. Questions? So the loss function that you are going to have is this different loss. So x and an x, I want them to be exactly the same. And on the other side, I want the divergence, which is in this case KL divergence, between PZ, this is the distribution of Z, which is the normal M and V. This is QZ, this is your reference distribution, 0 mean unit variance. You want this divergence to be small, right? So you're going to add it to your loss, and this is going to be your loss. What is the divergence? The typical divergence, as I said, is KL divergence. This is the expression for KL divergence, okay? And what you can see here, if PZ and QZ are the same thing, okay? So instead of PZ, I have QZ. Then it's going to be QZ divided by QZ. It's going to be 1, right? And log of 1 is 0. This integral is going to be 0, right? So KL divergence is non-negative. And when it's 0, it means that your distribution are exactly the same. Okay? Everybody's clear? So you're going to put this extra constraint here, and then that's it. So this one that you compute at the end of the day is going to be a function of that mean and variance you computed. You take this guy and put it here, and then you simply do backpropagation, right? You start from the output, you just backpropagate to the latent. In the latent, these two guys are going to show up through this extra term, and then you keep on going backward till you get your input, right? And you compute the sample gradient. You set the loss to be this one, you try to minimize it, and when you minimize it, you make sure that you are recovering your image perfectly, and at the same time, whatever you are getting at your latent PZ is actually being a normal random variable with mean 0 and variance 1. Okay? And this is going to resolve the issue for you a lot, because now if you want to do the training, okay, this is basically the training. So again, as before, like in a sparse autoencoder, you're going to just compute the gradient here, you move backward, you get here, and then when you get here, you have your normal back propagation, plus one extra term, which is including this m and v. This is going to let you carry lots of information towards input. And then once you have the gradient of the all weights inside this architecture, you are going to update. So that's going to be this, right? But now the key point here is that, maybe I just take this off, right? Now, if I want to generate with this architecture, what should I do? That is now very easy. I just generate one random Gaussian variable, 0 mean unit variance. I pass it through the decoder, I'm going to see 1/8, right? So the point here is that I am not messing around with this guy, which I cannot find it out. I am making my decoder to somehow behave like is looking at that unit variance 0 mean Gaussian variable, and it can generate 8, right? Because this space is not in my hand, right? I can do nothing about this, but the decoder is in my hand, right? So I am convincing it, okay, you just look at random mean unit, 0 mean unit variance Gaussians and try to generate 1/8 out of it, right? So you start from a noise, the image is pure noise, right? And then that decoder is gradually getting trained to, starting from a noise, give you 108, right? You got the idea? Questions? Yep.
Do we like apply the KL divergence, or will it force the M and V to be close to 0 and 1?
Yes, yes. This is going to be, right? I mean, this guy is going to be 0, this term, whatever f you compute. When m is 0, this guy is 1. Because essentially q is that one. This is normal 0 mean unit variance. This is normal mean m unit variance v. Then it's going to be 0 only in that case. You can write it down for one-dimensional Gaussian, you're going to see. When mu is 0 and variance is 1, then that's it. You can try it at home. Just put one Gaussian distribution with mean mu and variance sigma squared. The other Gaussian distribution with mean 0, variance 1. And then compute this expression. This is going to be super easy in that case. And then once you found this expression, you're going to see mu equals by 0, variance being 1, then this expression is 0. And for any other thing, it's positive, which is a property of KL. Yeah.
For VAE, are we still able to get the compressed dimension?
Yeah, I mean, that dimension is usually very compressed, the latent.
Dedicated to the given.
Yeah, but you are compressing it into a Gaussian random variable because you want to generate afterwards. If you want to just do compression, vanilla autoencoder is better than this one. This one is better when you want to do data generation, of course. Yeah. Yes. Maybe I finish and then we discuss it, right? So, so this is going to be the training. One final remark that I want to tell you, I mean, I said at the beginning, so this whole idea comes from the idea of variational inference. It means that you want to just somehow construct the Bayesian estimator of your data distribution, but you don't know what is the distribution of the latent space. Then you're going to assume this is Gaussian, and then you try to just develop the whole Bayesian framework with that assumption. This is what we call it variational inference, because we are considering a variational assumption or postulation as compared to the true one. But then you can show that variational result going to lower bound the original result. So what I say, it might be totally nonsense for you right now, but just wanted to tell you this variational term comes from that fact. And the right way to think about it is that we think of the neural networks as the machine, which are, I mean, the discriminative models, the models which are learning the conditional distribution. Then we need a prior, and we assume the prior to be Gaussian. And then at the end of that, when we realize everything with autoencoder, it's going to be the variational autoencoder. So this is something that you might get when you study generative models. But for implementation, that is totally fine. So for implementation, you can exactly do whatever I said in the previous slide, and you're going to be able to generate handwritten 8, right? The only issue here is that you don't know why you should generate those Gaussian random variables and why you should compute that KL divergence. If you study those, variational inference stuff, you're going to start to understand that. So that's it. Okay, I'm happy that I could finish it in time. So a few things, just the last things I want to mention here. The first one is that, I mean, you have pretty much any tool that you need for deep learning. I mean, from now on, it's only practice, and the fact that you should be always online. Yeah, you are not going to be like finished.